Today I'd like to show you how to use Kirchhoff circuit rules to solve circuits that are a little more complicated than the simple circuits we've looked at before. So remember the junction rule that says whatever current goes into a junction has to equal the current that comes out. So current 1 would equal current 2 plus current 3. Remember the loop rule that says whatever voltage we gain in the battery, we're going to lose as we go through our resistors. The net change in voltage should be 0. Okay, so take a moment and draw this circuit. It is neither our simple parallel circuit, nor is it our simple series circuit. Okay? So, how do we deal with it? Well, one way we can deal with it is to apply Kirchhoff's rules. So we're going to start here, walk through our battery, take the top path, and complete our first loop. We gain 24 volts in the battery, and that means we're going to have to lose 24 volts in our resistor. We now have voltage and current, so we can use Ohm's law, and we can get a current of 2.18 amps flowing through that top branch. That was easy. This one's a little harder. Let's start at the same spot and let's walk a different loop. Let's take the bottom path, complete our loop. We gain 24 volts in the battery. That means we're going to have to lose 24 volts as we go through the two resistors on the bottom. Realize we're not losing 24 in each, we're losing 24 total. So for that bottom branch, we have a voltage of 24, and since we're going through both of them, we are going to add them up, get 129 ohms. We're then going to divide using Ohm's law, and we're going to get a current through this bottom branch of 0.186 amps. Because it is a straight line circuit, we are going to have the same current going through all parts of it. There are no junctions that involve more than just one in and one out. Okay, we now know the current. We know the resistance. We can use Ohm's law for each one of these. And we can find the individual voltages. We get about 10 volts here. And we get about 14 volts here. You can see they beautifully add up to the total of 24 that we were supposed to get. Finally, if we wanted to find out how much current was entering into this parallel part of our circuit, we look at the current going in and set it equal to the current coming out, which is these two. We would add them together, and we would get a total of about 2.366 amps. That is the current that came out of the battery. It split into two. More took the top because it had less resistance. It joins back up again, and 2.366 would enter back into the battery. We could see we use junctions and we use loops to figure out what is happening in that circuit. Okay, a little bit more complicated this time. This time we have these two in parallel, and together they are joined with the 800. I'm going to label this voltage 1, voltage 2, voltage 3 for my three different resistors. I'm going to have current 1, I'm going to have current 2, and I'm going to have current 3. Okay, so let's take our time and do some loops. So loop number 1, I'm going to start here. I'm going to gain 9. I'm going to pass through resistor 1. I'm going to take this top branch, and I'm going to return to where I started. I gained 9, and then I lost voltage 1 and voltage 2. So voltage 1 and voltage 2 have to equal what I gained, so that I would have a net change of 0. I'm then going to take the other path, so I'm going to start here, go through the battery. I have to go through R1. This time I'm taking the bottom path, and I'm returning to where I started. So this time, gain 9, lose V1 and V3. So these are two different equations that conform to Kirchhoff's loop rule. I hope that you could see that this implies that V2 is the same as V3. Okay, I'm now done with loops. I now want to do a junction. So I'm going to do this junction right here. What goes into that junction is I1. What comes out of that junction is I2 and I3. This is where things are going to get a little bit confusing, so take it slow. Pause and rewind if necessary. I1 should be V1 over 800 according to Ohm's law. Voltage divided by resistance equals current. So instead of I1, I'm writing V1 over 800. I2 would be V2 over 180. I3 would be V3 over 570. Well, it looks pretty complicated, but we also know that V1 and V2 are the same thing, so I'm going to write it. V2 over 180 plus V2 over 570. That gets rid of one of my variables, and now I have two variables, V2 and V1, so I'm going to need to do some fancy algebra. We can't just add these two together because they have different denominators. But what we can do is multiply both sides by 800. Get rid of the 800 on the left. I would then just have V1 equals 800 V2 over 180, and I would have 800 V2 over 570. Again, I can't add the denominators, but I could turn them into decimals. So I'm going to do 800 divided by 180. I'm going to get V1 equals 4.44 V2 plus 1.40 V2. I now have V2 and V2, so I could add. V1 equals 5.84 V2. Still, I have too many variables. I have V1 and V2, two different variables. But I can substitute this into my first loop equation. So I could say 9 equals V1, I can call 5.8 V2 plus V2. I can now combine these together again and get 6.84 V2. And I can solve for V2 through simple division. And I get a voltage of 1.316 volts. We know that V3 is also the same voltage. V2 equals V3. And now we can plug this 1.36 back into either of these equations. Okay, so I'll switch back to green and say 9 equals V1 plus 1.316. I could then solve, and I get V1 as 7.68 volts. Okay, I now have my voltages, 7.68, 1.3, and 1.3. At this point, this is volts. At this point, we now can solve for I1. Volts divided by resistance, volts divided by resistance, volts divided by resistance, and get our currents. Okay, so a little bit more challenging than things we've done before, but hopefully you see how we progressed. We did a loop, we did a loop, we did a junction. We then did some algebra and figured out our voltages. We used our voltages to get our currents. We can use our voltages and currents to get power if that is something we need to find.